Hi, let's talk roots and radicals. In this lesson, that's exactly what we're going to do. Very similar to square roots, but we're going to go a step further and talk about roots that are more than just square roots, but can be cubic roots or fourth roots or fifth roots, and simplifying those. So if you want to, you can read this formal definition. And as we go through this lesson, I want to, first of all, just make sure we understand all the players here. First of all, you have the radicand, which is the number that is underneath the radical symbol. You have an index number, which actually tells you how many of that root number you have to have. For example, 16 can be written as 2 to the 4th. This fourth root and this 4, of course, are inverses of each other, so they cancel each other out. So 2 is the principal root. Now, what we're going to do is we're going to simplify roots by going through a few examples. First of all, again, what you want to do, let's just basically review square roots. With square roots, we really just kind of have memorized these perfect squares, but in essence, we can write them as 4 squared, and again, the square root symbol and that square cancel each other out, so our principal root is 4. With 8, the same thing. We can write it as 2 cubed, and again, this cube root and this 3, exponent of 3, cancel each other out, so 2 is the principal root. Now with odd number index numbers, keep in mind you can have negatives underneath the radical sign and they still be real because you have 3 equal factors. When that number is even, you will never have equal factors. So with that being the case, negative 27 can be written as negative 3 times negative 3 times negative 3. And when we remove the radical sign and the cubic root, we get the principal root, which is negative 3. Same can be done with exponents and variables. So again, this fourth root and this 4 will cancel each other out, and so we are left with just the principal root of x. Now what we're going to do is we're going to look at several examples of how to simplify. In this first example, you see the fifth root of 64x to the 7th. Now this could look very complex, but really I'm going to try and break it down as much as I can so you can understand it. First thing I'm going to do is I'm going to take that 64 and I'm going to separate it out from the x to the 7th. And since I want the fifth root, what I need to do is break this 64 down into its prime numbers. So to do that, pull it off to the side and just break it down into its primes. And eventually you will probably memorize some of these, but for right now, we know that 64 is equal to 2 to the 6th. Well, because I'm looking for the fifth root, then what I'm going to do, instead of writing 2 to the 6th, I'm going to write this as 2 to the 5th times 2 to the 1st. And as you can see, this is equivalent to 2 to the 6th. I'm going to do the same thing with this x to the 7th. I can break this up into 2 pieces, one being x to the 5th and the other one being x squared. And now let's pull these back underneath the radical symbol. And I'm going to, again, just separate out the ones that are perfect fifths from the ones that are not. And so under one radical, I'm going to put the 2 to the 5th and the x to the 5th. And in the other radical, I'm going to place the ones that are not perfect fifths. In other words, they're just kind of the leftovers. Now, again, as you saw in the previous examples, you can just take or remove the 5s off of this because the fifth root and these raised to the 5th power, they cancel each other out. And so your final answer will be 2x times the fifth root of 2x squared. I realize these take a little bit of practice, but hang in there because you can do these. Okay, let's do the same thing with the second example. I'm going to first just play with the numbers and the variables and regroup them. So again, what you may need to do with your numbers is pull them over and just break them down into their prime factors. And so again, we can see that 16 is equal to 2 to the 4th. Now, since we're trying to find the cube root of these, we are going to write this as 2 cubed times 2 to the 1st. And we're going to regroup this as x cubed times x to the 1st. And now let's put the radical signs back into play. And only the ones that are perfect, oops, let me just erase that 5. That's from the last question. Only the perfect cubes can go underneath the first radical. And then the second radical will be what I'm going to call our leftovers. And that's the 2 and the x. And now once again, when you take the cube root of 2 cubed x cubed, those 3's just cancel each other out, and you're left with 2x times the cube root of 2x. Now I'd like for you to try this next example on your own. If you want to stop the video and then start the video to see if you came up with the same thing that I did. All right, so again, we're going to take that 32 and that b to the 6th, and we're going to regroup those. Again, 32, you'll have to play around with a little bit. And you want to break it down into primes. So we know that this is going to be 2 times 16, and we just did 16 in the last problem, and we got 2 times 2 times 2 times 2. So 32 is equal to 2 to the 5th. And since I'm looking for the 4th root of this, I will write this as 2 to the 4th times 2 to the 1st. And then for b to the 6th, I'll write this as b to the 4th times b squared. And again, I'm going to take these perfect 4th roots and place them underneath the same radical symbol. And the leftovers will go in underneath another radical. And now again, these cancel each other out. These are inverse operations of each other. So the 4's disappear, and the roof of that radical goes away, and we're left with 2b times the 4th root of 2b squared. And that will be the end of this video.